Hello everyone, I welcome you to my lecture on shape memory composites with conventional constituents. I'm Gokul Ganesh Murali from Imperial College London. When we speak of shape memory composites, we normally tend to think of some structures that have shape morphing capabilities. So let me talk about shape morphing structures, but within Department of Aeronautics, so I'll talk something about aircrafts. So morphing structures are nothing new in aircrafts. Right from the first aircraft ever created, the Wright Flyer, to some modern military aircrafts like Mirage or like the supersonic passenger aircraft Tupolev or even Concorde, they all have morphing structures such as morphing wings or morphing nose and things like that. The main purpose for these structures is to improve the efficiency of the aircraft. All these structures until now have been using hinges and mechanical moving parts along with motors, servo, etc. to impart this behavior. But what does the future look like? So some of the concepts created by NASA, for example, thinks of emulating birds. So it will have some kind of complex structures that will be able to morph similar to birds. So for example, the wing should be able to twist, sweep, etc. There are several technological limitations currently to realize this phenomena. One such complication is limitation of active materials. So what are active materials? So they are the materials that are able to respond to some kind of stimuli, and for example, a shape memory material. So let us look how composites can be used for this behavior. I'll show you 5 different approaches where composites have been shown to display shape memory behavior. For example, let us first look at a bistable composite. What is a bistable composite? A standard cross-ply laminate consisting of just a 0 and a 90-degree laminate without any symmetry can have bistability. So these composites have more than one stable states. They have more than one low energy states. For example, in the picture on the bottom right, you can see a composite, a bistable composite, going from one low energy stable state to another low energy stable state using a piezoelectric actuator. And there have also been research where these composites have been used along with some flexible wings to create a structure that are able to morph as shown on the bottom left. Another type of composites that can be morphed are shape memory alloy actuated composites. Shape memory alloys are nothing new. They are a kind of metals that can store their initial shape and then recover it upon some kind of a stimuli, usually temperature. For example, nitinol, it is a nickel titanium alloy capable of doing this. On the right side of the slide, you can see some kind of shape memory alloy actuated composite, but with soft matrix. So it has a soft matrix and a shape memory alloy core using which it can change its shape. But more conventional materials, such as the ones on the left, where they use shape memory alloys as actuators to just deform conventional materials in the chevrons or that covers the engines. Similar to shape memory alloy actuators, shape memory polymers can also be used. Shape memory polymers also behave in a similar way, where they use the intrinsic shape memory behavior to impart morphing characteristics. They also can be soft composites, such as the one shown on the right side. And on the left side, we can see how shape memory polymer can be used along with CFRP materials to create shape morphing structures. Here is a shape memory hinge that is capable of recovering its shape purely based on the shape memory polymer that is embedded within the CFRP layers. We could, moving away from the material behavior, we could also use the structural anisotropy to create shape morphing structures. For example, you can see a corrugated composite on the slide. These composites are flexible in one direction, but they are stiff in other way. Using these, using such an anisotropy, morphing structures can be created. For example, here is a wing structure made of a corrugated structure. It will be able to deform in one direction, but it will be stable in the other. But there's a small catch with these composites, that is the complexity of their manufacture. They require a complex mold to create such structures. And finally, I'll come to variable stiffness composites. So these composites use conventional materials. So in this presentation, I'll be concentrating a lot on them. So in the upcoming slides, I'll be talking about the working principle behind them. But basically what they do is that they can be rigid or flexible depending on the experiment condition that we have. And they can have multiple shapes. So if you bear with me for a couple more slides, then I'll describe these composites in detail. But before I do that, let us quickly look at how these different approaches are looking for us. Let's look at different parameters as either favorable or unfavorable for us from a structural approach. So a bistable snap-through composite, it has limited structural stiffness and limited number of shapes, but it uses conventional materials and it is quite easy to manufacture. Then when we look at shape memory alloy composites, they can have good structural stiffness and they can have multiple shapes, but they require some kind of special materials, which in turn tends to increase the cost and increase the complexity, but they can be easily manufactured, similar to shape memory polymer composites. And when we look at structural anisotropy composites, they have limited shapes, but they can be stiff. They are easy to, they are a bit difficult to manufacture, but they use conventional materials. But variable stiffness composites, they have all the favorable conditions that we need for a structural composite. So how does a variable stiffness composite undergo shape morphing? So we have a variable stiffness composite. Let's take a flat composite. What it does is that when we reduce the stiffness of the composite and we deform it, it will deform to a large extent. But when we restore the stiffness of the composite and then we try to remove the deformation forces, the composite, because now it is in high stiffness state, the composite shape will be retained. So all the strain will be stored inside as an energy. And then when we try to release the energy, its shape will be recovered. Now, the key point here is that you could notice that I'm saying that we should play around with the stiffness of the material. But how can we do that? How can we play around with the stiffness of a material? A stiffness of a material consists of two aspects within the domain that I described. First is the flexural modulus of the material, and then the cross-sectional area. So their product gives us the flexural stiffness. Modifying flexural modulus is a material phenomena. Let's not go into that now. Let's try to change the composite by changing its moment of inertia. That is, if we decrease the thickness of the composite, effective thickness of the composite, we can reduce the stiffness of the composite. So you might think reducing the thickness of a composite might not be very easy. So we can try an innovative approach, that is using interleaved composites. So interleaved composites consist of conventional CFRP plies interleaved with thermoplastic polystyrene plies. These composites have some special behavior, special characteristics. Let's consider a simple interleaved composite consisting two CFRP plies interleaved with one polystyrene ply. If we try to bend them, they have certain flexural stiffness and they will resist deformation. But when we heat the composite beyond the glass transition temperature of the thermoplastic material, what happens is the material becomes soft and the CFRP layers will slip with respect to one another and overall stiffness of the composite drops drastically. And then if we again cool down the composite, the stiffness will be restored. Using this phenomena, we can further make these composites to show shape memory behavior like this way. So initially, the composite will be in a flat shape and it will have no internal stress. But when we heat the composite and we deform it, stress will be formed within the CFRP layers and not within the polystyrene layers. Now, when we cool down the composite and we remove this load, the composite now in its high stiffness state will not be able to release the stress. The composite wants to release it, but the high stiffness does not allow it to release. So when we again heat the composite and reduce the stiffness of the composite, all these stresses will be released and the composite goes back to its initial shape, thereby effectively showing a shape memory behavior, even though the composite does not have any special materials. Let me show you a quick video of a composite showing all these behaviors. Here's a composite in 3-point bend setup. Initially, when we load it in room temperature, there's a certain force against displacement slope, as you can see. But when we heat the composite and repeat this experiment again, we can see that even for large displacements, the slope remains very shallow. That is, it does not develop large stresses. And then we can also see a quick shape recovery. I'll show a detailed video of this later. And then after shape recovery, when the composite is cooled down and tested again, its original stiffness is fully restored, as shown here. Now, let us look at how the stiffness behavior changes. I told you that stiffness drops drastically. Let's see how drastically it drops. Like when I test the composite first at room temperature, and then I heat them at 120 degrees Celsius, and then test them again in the flexural test setup, and then I again test them at room temperature, just to see how the stiffness can be controlled. And from the load displacement diagram, you can see that by heating the composite, the reaction force of the composite in the flexural test setup drops by around 3 orders of magnitude. And then upon cooling the composite again, we can see that the initial stiffness is restored. That is, the force displacement graph goes back to its original pattern. Now, looking at the flexural modulus of these composites rather than these graphs, what we can notice is that for control composites, we can see that is a composite made of just CFRP. We can see that the heating the composites does not cause any change to the flexural modulus. But when we interleave the composites with with polystyrene or any other thermoplastic material, we can see that the modulus of these composites drop from around 66 down to 0.3, and then it goes back to 66 upon cooling. So this is what we want in an interleaved composite. And when we look at the shape memory behavior of these composites, so the steps now involve, we take an initial composite when it's pure and flat shape, we heat the composite, we deform it, it undergoes deformation, and then we cool down the composite and then remove the load, it retains its shape, and then upon heating, the composite shape will be recovered. Let me show you physical pictures of it. So here we initially take a composite in its flat shape, then we heat the composite and then deform it, and then we cool it down, the shape will be retained, and upon heating, the shape is recovered as shown here. The video is 8 times the speed, so you can see it takes around 3 minutes for this shape recovery to occur in real life. So these composites show shape memory behavior. Now let us see how these composites can be used for some kind of morphing structure. So before that, we also did one more work on these composites. That is, previously all the temperature necessary for this was supplied by an oven, as shown here. But this is not practical if you're going to use this in field or if you're going to use it outside the laboratory. So what we did is we embedded some kind of a stainless mesh inside the composite and tried to heat the composite through direct current, and it worked well. So ideally, in future, we could just make composites, embed heating element, and then take it anywhere in the world and just apply current and it will deform. That's the idea. So looking at structures, what's been previously done is that a composite like this, a flat shape, was manufactured and then it was heated, and then when it was pulled apart, it formed a mesh structure like this, and upon cooling, the structure was retained, and then upon reheating the composite, it returned to its original shape. It worked well, but ideally what we expect from a shape deformable structure or a deployment structure is that it should go directly from a flat shape to a deployed shape without any intermediate step required from us. Doing this is quite simple. So we have the four stages of shape memory study involving two steps. We have a shape fixing step and a shape recovery step. What we need is to eliminate these two steps. So we need to eliminate these two steps and directly go from an initial stage, an initial cured stage, to a deformed deployed stage. To create this, we need to have some kind of stress formed within the composite just by curing it. How do we do that? We can look at generating residual stress within these composites. Residual stress, initially we are, so to create these composites from a flat to a deployed shape, we need to have a repeating unit like this deformed shape. So, yeah. So how we achieve this is by having 0, 90 and 90, 0 layer. So if we have this layer, then this mismatch of coefficient of thermal expansion in 0 and 90 degree will deform the composite into a shape like this shown on the slide in its cured state. But that's not what we want. We want a composite to be flat when we cure it, and we want it to deform only when we want it. So this is where interleaving again comes into play. So when we interleave these composites with polystyrene, what happens is the stiffness of the composite now goes so high that the composite wants to deform, but because of the high stiffness, it will not be able to deform. So it will initially stay flat when we cure it, but then upon heating, the polystyrene layer will soften, and the CFRP layers, the pairs of CFRP will be free to deform, and we could achieve shape deformation like this. Here's a quick video showing shape deformation from an almost flat shape to a mesh shape. Now, when we look at more practical structures, they're not just straight, to use straight measures. In reality, structures have bends, they have curves. So what we need is to create some kind of a deployable structure that is also capable of curvature. I will be talking about this in my conference presentation in a couple of days. So I'm going to just glance through these for now. So for this, we propose a layer, a repeating layer shown like this, which is consisting of a 0 degree CFRP and then interleaved with CFRP with certain theta degree orientation. So using this, the composite can be made to undergo twist. And when we look at just the repeating section, the highlighted section, it has certain deformation parameters. And using this, we can arrive at some deployment parameters such as the expansion ratio and deformation angle. Expansion ratio tells us how big our composite will go from its flat shape to a deployed shape. And then the deployment angle will tell us how big our curvature or how small or how sharp our curvature can be of this composite. Now, when we change the theta parameters, for example, when we take a 090 composite, the rightmost set of data, it will be a cross ply, and the composite will not be able to twist. It will just go from a flat shape to a mesh shape. And then by changing the theta, everything can be changed, and you can, depending on what kind of mesh you want, you can select the theta that you want, and it can be achieved. So here's a small experiment that we did, some initial trials where we created a composite. When it was cured, it was almost flat shape. It did not fully retain its flat shape. But then upon heating, we could see the composite deploying in a curved path. And just to visually see how these composites will look, we just attached them together, and then we saw a curved deployment composite. So what does the future hold for us? So we can think of creating deployable structures capable of intrinsic heating, so that we can just take a layup somewhere and then just deploy it. And we can also create complex structures. Now we have now we are able to create straight deployment and curve deployment. So now you can just use your imagination to create more complex structures. There are some technical limitations, but this can also be done. And then we could also investigate on using different material combinations. For example, different grades of thermoplastic. Instead of CFRP and polystyrene, we could think of different grades of reinforced thermoplastics interleaved with some thermoplastics with lower glass transition, for example. With that, I would like to conclude my presentation, and I'm open for questions.